Okay, this is Crash Course on Factoring. Again, I'm going to just go fast. If you want to take notes, you may. If you just want to listen, you may. It's recorded. But I'm going to go real quick. So, factoring. Any number or value or term can be expressed as the product of its factors. Okay, you need to get these terms straight. Factor times factor times factor times factor. Anything you multiply is a factor. Okay? And when you multiply them all together, the answer is a product. Okay? You can also split your product into factors. Okay? Here we go. A couple examples. Real straightforward. What did I just say? Any number can be expressed as a product of its factors. So 4 could be 2 times 2. Right?
Yeah.
And x cubed could be x times x times x. This is 3 factors of x that make up x cubed. Okay? Something like 8x as a number and a variable can be expressed as the product of its factors. I could break up this 8 into 2 times 4. This is an expression that has the exact same value as 8x. It's split into 3 factors. I could split it further because I can split this 4 up into 2 times 2 times 2 times x. Now it's split into its prime factors. Okay, this is the smallest factorization you can do with 8x.
We're done. No,
That's a wrap.
like X.
When working with 2 or more terms, the goal is to find the factors that they have in common. Okay, when you're working with 2 or more terms, the goal is to find the factors that they have in common. So let's say we're working with 6 and 18. Well, 6 can be expressed as 3 times 2. 18 can be expressed as 3 times 6.
Or 3 times
So
4.
now you could say that they have the factor 3 in common. But you say, oh, Mr. V, you can actually split this into 3 times 2 times 3, because 2 times 3 is 6. Now all of a sudden they have 3 times 2 in common, and then you would say, we actually just found that the greatest common factor between 6 and 18 is 6. And we could go even further, and we could say, well, let's express each of these numbers as the product of 2 factors where one of those factors is the greatest common factor. So we can take 6 and we can express it as a product of its factors where the first factor is 6. 6 times 1 is 6. So let's look at what 18 does. We take out the greatest common factor. We still have 3 left as another factor. Okay, let's get a little bit trickier. Let's go for x to the power of 4 and x to the power of 3. Well, we split these each into their factors. We find out that x to the power of 4 is just 4 factors of x. X to the power of 3 is 3 factors of x. So you say, oh, Mr. B, look, they have 3 factors of x in common, which tells me that the greatest common factor between x to the power of 4 and x to the power of 3 is x to the power of 3. Oh, let's take each of these terms and express them as a product of 2 factors where the first factor is the greatest common factor. What times x cubed is x to the power of 4?
X.
One more factor of x. What times x cubed is x to the power of 3? 1. Excellent. Thank you very much. Let's get a little bit trickier here. Let's go for a pair of values, a pair of terms that has a number element and an exponent variable element. We've got 2x squared and 10x. And let's break these into their prime factors. Well, this is 2 times x, right? 2x, x. What about 10x? 2 times 5 times x. All right, let's take care of these factors they have in common. They both have a 2 and they both have at least one x. So that tells me that the greatest common factor between these two terms is 2x. Okay, let's express each as a product of factors where the first factor is the greatest common factor. Well, 2x times what gets 2x squared? Another factor of x. 2x times what gets 10x? And a factor of 5. And that's just the missing factor that we hadn't tackled from each term right there. Makes sense? And you can look at that all the way up. Here's the last one, so we had to multiply by an x. This one still needs to get multiplied by 3. There it is. This one, there's nothing left once I pulled out the greatest common factor of 6. But I still have to multiply by something because I needed 2 factors. If I multiply by 1, I'm good. Okay? Okay, let's try that same strategy, pulling out a greatest common factor, but now using a binomial. Now I don't just have 2 terms. They're actually attached in a chain of addition and subtraction. They are not like terms. I have x to the power of 4s and x to the power of 3s. I can't just add them up. I don't have 2 of anything. Okay, so don't do that. But what I can do is I can factor out the greatest common factor. Now, in the previous step, we already decided x to the power of 3 was the greatest common factor of each of these. So let's express x to the power of 4 as a product of 2 factors where the first factor is the greatest common factor here. All right, there's x to the power of 4. There's x to the power of 3. Now you'll notice these are still 2 terms. They have a common factor of x to the power of 3, but watch what's happening. X to the power of 3 is being multiplied by x. Then it's being added to x to the power of 3 being multiplied by 1. Watch what happens if I rewrite this as a product of 2 factors. I'm going to pull out my common factor, and I need to make sure x to the power of 3 is getting multiplied by x, and it's getting multiplied by positive 1. There it is, factored form. Okay? Let's do another one. This time I'm going to put it in an equation. We're going to say it's y equals 2x squared plus 10x. Now these are the same 2 terms that we worked with in the previous step, 2x squared and 10x. But this time they're attached by addition or subtraction. They are a binomial. What do? Well, I find the greatest common factor between them, which I already decided in the previous step was 2x. This term is 2x times x. This term is 2x times 5. So now you can see that when I'm factoring this, 2x is being multiplied by x, and it's being added to 2x times 5. And both of those things are represented right here. 2x times x, 2x times 5, addition, addition. Okay? Now why would anyone ever want to do this? Well, this tells me on a graph the value of y with respect to x. So as x changes, y changes. That's why we get curves and lines and everything that we can draw on a graph. As x changes, y will also change. But what this allows me to do is find specific values of x that match specific values of y. Now that doesn't sound like that great, but some values of y are really important. Like for instance, where does y equal 0? Well, that's this whole line right here. That's important for us to find out where the value of something is 0. So how do I actually figure that out? Well, this is the goal of factoring in a lot of cases, is to find your zeros. The place where the curve crosses the x-axis is the place where y equals 0. So really all I need to do is sub y in for 0. And then I have my 2 factors. And I know that when I multiply anything by 0, it will equal 0. So this tells me that for the whole thing to equal 0, either 2x equals 0 or x plus 5 equals 0. Okay? Now, this I divide both sides by 2. I get x equals 0. So I know that this function equals 0 when x is 0. So it actually goes through 0, 0. When x is 0, y will be 0. What about this one? Well, subtract 5 from each side, x equals negative 5. Okay? So this function will equal 0 when x equals 0 and when x equals negative 5, which tells me that this looks something like this. And if you're really good with completing the square, and you can do it in your head mentally, you'll actually know that this down here has a minimum at negative 25. So that's why we would be factoring, and that's how to factor. These are the very basic, this is the basic factoring. The first thing you're going to look for, is there a common factor? Pull it out. Okay, those ones were not so tough because we just pulled out a common factor, but let's say you're looking at your page and there's this polynomial there. It's a trinomial, 3 terms, and it's a quadratic because the highest power of x is 2. And you're looking at this thing and you're saying, okay, I've got 1, 2, 3 terms, and there's no number in common and there's no variable in common. Well, what do I do? And that's exactly right. You go down your list and you say, okay, 1, is there a common factor that I could pull out of all 3 of these terms? In this case, no. Is this thing a pattern that I've seen before? Is there a pattern like a perfect square? Perfect square. Maybe a sum and difference. And to all of those, no recognizable patterns here. Well, then the next goal in factoring this is you have to recognize what the completed factorization is going to look like. So what you're going to have at the end of this, if it's none of these, then you're going to have 2 binomials multiplied together. And inside each of those binomials, you have an x as the first term. And there's going to be 2 other terms, one here and one here. Okay? You should be able to recall that factored form is x plus r, x plus s, right? So we're looking for 2 numbers that are going to fill in these space. Well, what are the characteristics of those 2 numbers? We are going to find 2 numbers such that last times last equals 12, and outside times outside plus inside times inside equals 8x. And explain that. In order to talk about it, why don't I just put some letters in here. Let's say this is plus r and this is plus s. Now we can start to see that if we FOIL this out and we go first times first, it's going to end up with x squared. And then we go outside times outside, inside times inside. I'll talk about that in a second. But let's talk about what happens when we get last times last. R times s. Well, that's going to result in the only term with no x in it. No x here, no x here. R times s is going to be our constant term. Okay? So when I'm talking about this last times last, that's going to be r times s equals 12. Let's talk about this part. Outside times outside is s times x, which is sx. Inside times inside is r times x. It's going to be rx. Again, that equals 8x. So you can see already these are the 2 terms that on our expansion are going to combine to make this x term, 8x. Well, let's just look at this little piece here. Basically, I have a common factor here of x, and here I'd be left with an s plus r. So s plus r is being multiplied by x, and that's going to get us 8x. And now you can see if I'm reducing this further, I can divide both sides by x, and s plus r equals 8. So now you can see that these two numbers that I'm looking for, r and s, those same two numbers are going to multiply to 12, and they're going to add to 8. And those 12 and 8 comes right from our original equation. Two numbers that have a product of 12 and a sum of positive 8. I'm going to write that down, okay? So we're looking for two numbers that have a product of 12 and a sum of 8. And so that's where we get the idea of a sum and product chart, or a product and sum chart. I'm going to run through that now. Where we have a product of 12, a sum of 8. I'm looking for two numbers that have a product of 12. I'm going to start on this side because I could come up with an infinite list of two numbers that add to 8. An infinite list of positive and negative numbers that will add to positive 8. Okay? But there's a limited number of factors of 12. So I'm just going to go ahead and list them. 1 and 12, negative 1, negative 12. 2 and 6, negative 2, negative 6. 3 and 4, negative 3, negative 4. That is all of the factors of 12 paired up. And let's see what they add to. 1 plus 12 is 13. It's not going to work. Negative 1 plus negative 12 is negative 13. That's not. We're looking for 8, right? The sum of 8. 2 plus 6. That equals 8. I wonder if we'll find any other factors of 12 that add to 8. Negative 2, negative 6, negative 8. Nope. 3 and 4 is 7. That's close, but nope. Negative 3 and negative 4 is negative 7. Nope. So there's only one possible solution here, and it is the factors of 2 and 6. So I can go straight from my polynomial here, find two numbers that multiply to 12 and add to 8, and they become the two numbers that finish out my binomials here. And if I want to double check, I can go ahead and multiply this back in my head. X times x is x squared. X times 6 is 6x. 2x here, that adds to 8x, and 2 times 6 is 12. Okay, let's run through this example a little bit more quickly. Again, first, am I going to look for common factors? No. Any special patterns? No. So I'm looking at sum and product. I've got a product of C, so I'm looking for two numbers. I'll multiply to negative 35, and I will add to negative 2. Let's run through my list of factors. I've got 1 and negative 35, because it's going to be a negative number, right? So I could also have negative 1 and positive 35. Then I was 35 divisible by 2, no, divisible by 3, no, divisible by 4, no, divisible by 5, yes. Its pair is going to be negative 7, or I could have negative 7. Sorry, negative 5, positive 7. Now, let's see what these guys add up to. Negative 34, no. Positive 34, no. Negative 2, yes. Check this one just in case. 2, no. There will always only be one pair that makes this thing work. So I can come over here. I've got my product of two binomials. Throw my x's in. My other ones are negative 7 and positive 5. Does it matter where I put the positive 5 and where I put the negative 7? No, I could have swapped them. They're all going to get expanded out if I double checked. But this is factored. Okay? Well, why would we do this? Why would we ever want to factor something? Again, it makes it real easy. If I want to set y equal to 0, I can now find out exactly where this parabola crosses the x-axis. Okay? And I can tell that it happens over here. My chart's not very good. I'll draw that real quick. Okay? It happens over here at positive 7. And over here at negative 5. One more to run through here without a coefficient of anything greater than 1 or less than 1 in front of the x squared term. We just have a coefficient of 1 here. And I'm going to, again, there's no common factor here. There's no special products here. So I'm going to go right into sum and product. I'm looking for a product of negative 24. That's two numbers that multiply to negative 24. And those same two numbers have to add to 10. Now, I might be tempted to think about 6 and 4. Because, 6 and 4, a version of them multiply to 24, and a version of them add to 10. But it's not going to work out because positive 6 and positive 4 is what I would need to add to 10, but I have a negative number here. So one of these has to be negative. So whether it's this one or this one, that's the same. Whether it's this one or this one, doesn't matter. They're now no longer going to add to 10. So I need to look elsewhere. Turns out that 12 times 2 is 24. So one of them can be negative in each scenario. And I just need to pick the one that adds to 10. It's going to be, my bigger number is going to be positive. 12 plus negative 2 is 10. So I can right away go into my product of two binomials, x plus 12, x minus 2. And again, it helps me find out any value of y that I want, but usually, if you're in an equation like this, you're interested in finding out where y is 0, right? Because that will tell you exactly where your x-intercepts are. And because these are factors, and anything times 0 is 0, then either my first factor needs to be 0, or our second factor needs to be 0. And I can solve this out, subtract 12 from both sides. Here, add 2 to both sides. So the solutions are x equals minus 12 or x equals positive 2. If we did a quick sketch, it just means that it's a parabola that has an x-intercept over here at negative 12 and an x-intercept here at positive 2. And looks something like that. That's pretty wonky, but you get what I'm saying. Helps you find those x-intercepts. Well, what if I get a real tough one? Like, what if the coefficient in front of x squared is 3, not 1, like I'm used to? Well, I'm going to follow the same exact steps. I'm going to check, is there a common factor that I could pull out of all three terms to make this a little bit easier for myself? 3, 10, and 8, nothing with the numbers. X squared, x, and no variable? No common factor to help me out. Is there a special product here? Is, for instance, this a square number? No. It's not special. Now what I'm noticing, the coefficient is not 1. Okay? So the coefficient of the x squared is not 1. So I'm still going to use sum. So use sum and product. But it's not going to get me right down into my nice little answer of two binomials. It's not going to happen this time. Instead, I'm going to use sum and product to split the middle term. Okay? So, use sum and product to split the middle term. Now, when I use sum and product here, before we were looking for a product just of c. We were actually always looking for a product of a times c, but a was always 1, and anything times 1 is just itself. Now a is 3, so we're actually looking for a product of 8 times 3, which is 24. And those same two numbers that multiply to 24 are going to add to 10. Well, looky, here we go, we get to use our 6 and 4 after all. So the factors of 24, 1 and 24, 2 and 12, 3 and 8, 4 and 6. I'm going to ignore the negative values because I know I need to add to a positive number, but I could include negative 1, negative 24, 2, negative 12, negative 2, negative 12, negative 3, negative 8, negative 4, and negative 6, but I need them to add to 10, so I know I'm looking at positive numbers. These guys add to 25, no go. 14, no go. 11, getting closer. 10. Cha-ching. Alright, now, again, I don't just get to throw those into the product of two binomials. Instead, I get to rewrite my original expression, this time splitting the middle term. 10x, 10x, okay? This is now going to be called factoring by grouping. So what I'm going to do, I can't, again, find a common factor among all four terms. Nope, there's nothing special going on here, but now I can factor by grouping. So, group these two guys, group those two, and look at each of these groups, pull out a common factor here. The common number is 3, and they both have at least one factor of x, so I'm going to pull out 3x, leaving me with x plus 2. Over here, I can factor out a 4 from each term. That's the greatest common factor. It's going to leave me with x plus 2. Now I'm looking at this statement. I've got two terms, one here, one here. They have a common factor, x plus 2. X plus 2 needs to be multiplied by 3x, and it needs to be multiplied by 4. And there we have it. Again, if I wanted to follow this out and actually find the solutions here, this is just a quadratic expression. If I had this, now it's a quadratic equation, and I could solve it by setting y equal to 0, which tells me that either x plus 2 equals 0 or 3x plus 4 equals 0, because anything times 0 is 0. So the solutions, one of them is x equals -2. Over here, I'm going to subtract 4 from both sides, then divide both sides by 3. Find the other solution is -4/3. There's your crash course in factoring. We've done a handful. We did the common factor, taking out the common factor. We did factoring x squared plus bx plus c by finding two numbers that multiply to c and add to b. And then we did this last harder one where the coefficient of the x squared term is not 1, in which case we had to use sum and product, where we had the product of a and c, but all we could do was split the middle term, and then we used a strategy called factoring by grouping. Okay? So go ahead, watch this as many times as you need to, do lots of practice problems, check the back of the book, and you'll be ready to go. One more quick example. We're going to split the middle term using sum and product, then factor by grouping. Okay, so I'm looking for two numbers that will multiply to AC and add to B. So two numbers whose product is -30 and whose sum is 13. Well, go ahead and list all of the factors of -30. We've got 1 and -30. We've got -1 and +30. We've got 2, -15. Oh, I think I'm going to have a winner right here. -2 and +15. These guys add to 13. They will be the only two that do that. So here we go. All that's going to allow me to do is split this +13 into +15, -2. So we have 6m squared. I'm going to put my -2 on this side, so I have -2m's plus 15m's. That's going to give me my 13m's minus 5. And now I am factoring by grouping. So I'm going to go ahead and group these two. I'll just rewrite it. 6m squared minus 2m and 15m minus 5. Look at my first group, factor out. The greatest common factor is 2m, leaving me with 3m minus 1. Remember, it's what do I have to multiply back to get 6m squared? Well, that's 3m. What do I have to multiply by to get back to -2m? That's -1 times 2m is -2m. Okay, same thing here, greatest common factor. I'm going to pull out +5. I know I can pull out +5 because that's going to still leave me with a -1 here, which is what I have here. So I want them to be the same. I could pull out a -5, but then I would have different brackets and I'd have to do a little bit of more work. So here we go. 15m divided by 5 is 3m. -5 divided by 5 is -1. Now I look, I have two terms. Both of the terms have the group 3m minus 1, so I pull that greatest common factor out. What do I need to multiply to get this? When I've already pulled out this, well, I have 2m left. And out of this big term, what do I need to multiply by back to get it? When I've already pulled out 3m minus 1, I need to multiply by what's left, 5. There's my two factors, okay? And again, why do we factor? Well, this tells me that the solutions to this, right now it's just an expression, but if I set it equal to 0, now I could say, well, what does m have to be in order to actually get 0? Well, either 3m minus 1 equals 0, in which case I would add 1 to both sides, divide both sides by 3. Either m is 1/3, or 2m plus 5 equals 0. Subtract 5 from both sides, divide both sides by 2. The other solution for m is negative 5/2. And there you have it, crash course on factoring, all the different ways. And again, if you can't factor, if it's too hard to factor, you can always use your quadratic formula. Negative b plus or minus square root of b squared minus 4ac all over 2a. Okay? Not just this chunk over 2a, the whole thing over 2a. This will always work if you're stuck.